This video is about modeling a situation using exponential growth and decay models, predicting future outcomes using exponential growth and decay models, and using a graphing calculator to solve exponential growth and decay models. So remember again that when a quantity is growing exponentially, it's increasing over the same period of time, and we call this exponential growth. So remember, for our growth equation, we're going to have a plus inside our parenthesis where we're adding the rate to 1. So A is going to be our start value, R is going to be our rate, and T is going to be our time. Also remember that when we are doing dollars or years, we're going to round to the nearest hundredth. And when we're doing people or animals, we're going to round to the nearest whole number. So today what's going to happen is we're going to solve the problems, and we're trying to find the time that something's going to happen. So a newly hatched channel catfish weighs about 2 grams. During the first 6 weeks of life, it increases growth by 10% each day. So for our growth equation, we're going to have y equals, the start value is 2 grams, and then parenthesis, we can take this 10% and we're going to change it to a decimal, so 0.10. So we have 1 plus 0.10 to the t power. So inside the parenthesis, we can simplify that. So we have y equals 2 times 1.10 to the t power. So in this case now, it says how long will it take for the catfish's weight to double? So if the original weight was 2, when we double the weight, it's going to be 4 grams. So we want to know, when is the fish going to be 4 grams? So what we're going to do is we're going to take this 4 and we're going to substitute in for y. So when I write the equation, I have 4 equals 2 parenthesis 1.10 to the t power. So we're going to use our graphing calculator to solve for t. So we're going to go to y equals and clear out anything we might have in there. So for y equals, we're going to split this equation in 2. So y1 is going to be 4, and y2 is going to be 2 parenthesis 1.10 close parenthesis. Caret, now instead of having the t, we're going to use x. If you get confused, remember that x and t are on the same button on that diagonal from the second key. So x is going to be our exponent instead of t when we're graphing using the calculator. So now if we hit graph, we can see our picture, and we see an intersection of that blue and red line, which remember on your calculator might just be 2 black color lines depending on which calculator you have. So to find the intersection, it's just like we did in past chapters. We're going to hit second trace. We want intersection, so we're going to hit 5, and then we're going to hit enter 3 times. 1, 2, 3. So it says intersection, and that point then, we're looking at the x value for our answer. So we're going to have t is equal to, and we round that, 7.275, so the 5 rounds us up, so it's going to be 7.28. So how long will it take for the catfishes to double? Remember, it's happening by days as our unit. So our answer then is 7.28 days. In part B, it says how long will it take for the catfish's weight to be 10 grams? So this time we're going to substitute 10 in for y. So when we write that equation, we have 10 equals 2 parenthesis 1.10 to the t power. So in our calculator, we're going to go to y equals. The second equation's okay because it's still the same. We're going to change y1 though to equal 10 now. So when we graph, it's a little bit hard to see the intersection here. So we need to change our window because we need to go up a little bit, and we know it's somewhere over here to the right. So when I go to window, I'm going to change my x max to 20 so I can make it longer to the right. I'm going to change my y max to 20 so I can see a little bit higher. So when I hit graph, now I can see the intersection with my lines. So to find that intersection, I'm going to hit second trace 5, enter, enter, enter. So when I look at x equals, I see 16.886, so that 6 is going to round us up. So t is equal to 16.89, which is 16.89 days. Make sure that you are labeling your answer at the end of the problem. So number 2, you deposit $800 into an account that pays 6% interest compounded yearly. Write an exponential growth equation for this model. So we're going to have y equals, we start at $800, parentheses, when we do 6%, when we change that into a decimal, it's 0.06, so we have 1 plus 0.06 to the t power. So that simplifies to y equals 800 times 1.06 to the t power. So if it says how long will it take for your deposit to reach $15,000, we're going to put 15,000 in for y. So we have 15,000 equals 800 times 1.06 to the t power. So in our calculator, we're going to hit y equals 15,000 is our y1. y2 is going to be the other side of the equation, so 800 parenthesis 1.06 to the power of t, which remember we're going to use an x for. Now if I hit graph this time, I'm not really going to see anything on my graph. That's because we're dealing with bigger numbers here. So we need to go to y equals. We're going to leave our y max or y min at -10. Let's change our y max or x max to 50. Y min we can leave the same. Y max, so the biggest number in this problem is 15,000, so we need to go a little bit higher. So I'm going to go to 16,000 and I'm going to hit graph. So now we can see both of our lines. Now that red line's a little bit hard to see the intersection, so I'm going to go back to my window and I'm going to move the x max a little bit bigger to 60. So when I graph now I can clearly see the intersection. So now that I can see the clear intersection, I'm going to hit second trace option 5 and hit enter 3 times. So we get an intersection then of 50.30. So it's going to take 50.30 years for that money from the initial deposit to reach $15,000. So remember, when a quantity is decreasing exponentially, we're going to call that exponential decay. And the only difference in an exponential decay model is that it's a subtraction in the parentheses instead of a plus. But the variables still stand for the same thing. So a is still our start value, r is still our rate, and t is still our time. So in number 3, a summer youth camp has a declining enrollment from 1995 to 2005. The enrollment in 1995 was 250 people. Each year for the next 10 years, the enrollment decreased by 2%. Let t equal 0 represent the year 1995. So write a model for this equation. So this time we're going to do an exponential decay. So we have y equals, the start value is 250. If it's 2%, when we change that into a decimal, we're going to have 0.02. So we have 1 minus 0.02 to the t power. So that simplifies to y equals 250 times 0.98 to the t power. So in what year is the enrollment? 225 people. So we're going to take 225 and we're going to substitute in for y. So when we do that, we have 225 equals 250 times 0.98 to the t power. So to solve for that, we're going to use our calculator again. So y equals, we're going to have 250 for y1 and y2. Oops, sorry, y1 is going to be 225. And y2 is going to be 250 parenthesis 0.98 to the power of x. So this time, because I was just using really big numbers, I kind of want to change my window already. So I'm going to change my x max. I can leave it at 50, that's fine. My y max, though, is way too big because the highest number here is 250. And remember, we're decreasing, so our graph's going to go lower than that. So if I start at 300, I should have a good window. So I'm going to hit graph now. So I can see the intersection. So I'm going to hit second trace 5 to find the intersection point, and then hit enter 3 times. So we get t equals, and I have 5.215, so that 5 is going to round up. So 5.22, so it's going to be 5.22 years. In part C, it says, in what year will the enrollment be half? So if the original enrollment was 250, we can take 250 and divide that by 2 to cut it in half. So we want to know when the enrollment is going to be 125 people. So we're going to do 125 equals 250 parentheses 0.98 to the t power. So in our calculator, the only thing we need to change is y1, and we're going to change that to 125. The window is the same because it's the same type of problem, so we can just hit graph. And we see our intersection. So we're going to hit second trace 5, and we're going to hit enter 3 times. So we get that t is 34.31 when we round. So 34.31 years. So the next equation, you buy a car for $28,000 and the car depreciates, which remember decreases, at 9% each year. So we're going to write an exponential decay equation that models the situation. So we're going to have y equals 28,000 times 1 minus, and remember that we can write 9% as 0.09 for a decimal, so 1 minus 0.09 to the t power. So this equals, y equals 28,000 times 0.91 to the t power. So we want to know how long it's going to take for the cars to reach half its original value. So we're going to take 28,000 and divide by 2. So we want to know when is the car going to reach 14,000. So we're going to set 14,000 equal to 28,000 times 0.19 to the t power. So we're going to go to y equals, and in y1, we're going to put 14,000. And in y2, we're going to put 28,000. Parentheses 0.91 to the power of t. Now, we need to change our window before we graph. So the x's are probably fine for now. The y, though, needs to go way up because the highest number is 28,000. So we're going to go a little bit higher. We're going to go 30,000. We're going to hit graph. So we can see both of our lines. So to find the intersection, second trace 5, enter, enter, enter. And when we round that, we get t equals 7.35. So it's going to take 7.35 years for the car to reach half of its value. In C, how long will it take for the car to reach 7,000? So now we're going to change it so it's equal to 7,000. And we're going to do the same thing. So in our calculator, all we got to do is we got to change y1 to 7,000 and hit graph. So we see our intersection, so we can hit second trace 5, enter, enter, enter. And we get t is equal to 14.70. So we have 14.70 years.